So when we talk about the Six Sigma analysis aspect of it, right, there's a few considerations I want you to keep in mind as we're going through. Right, notice this still shows one half of the curve, but it's not highlighted. Well, that's represented in our data because we can see that this is going to be essentially 50% right off the bat. Because this only takes into account the shaded region, right? It doesn't take into account what the difference is. The reason I use this is what industry standards usually use as a chart, and I just wanted you to have this a little bit advanced knowledge, and plus you wouldn't be flipping through. In black belt, I mean, I can show you guys this, and you already have it in your chart, but in Six Sigma, we can use Excel or Minitab to understand it. So just take into account, we have 50% right off the bat that is not accounted for. And we know that because when we look at our data, it only shows the green region, right? But notice it doesn't show all of it. It doesn't shadow all of it. So, for example, if I said we have a Z value of 1.02, well, the way I would see this is I would go down to, let's say, 1.0, and then go over to 0.02. Well, that's going to give me 0.3461 as an answer. But notice, I still need to give my p-value, right? What's my probability as a whole distribution? So what do I have to do? Well, I have to take, essentially, this shaded region, I know it as 34.61%, right? So I want you guys to put it in the chat. What would be my probability as a whole distribution? You know, this is asking what's the probability of hitting the mark. So if I have 50% and I have 34.61, that leaves us with 84%. Now, keep in mind, this is our efficiency. This is our distribution as a whole. Now, what about this shaded region here? Well, this isn't where it gets super complicated. If I know that this whole distribution is out of 50% on this side of it, it's just going to be subtracting 50 from that. If I'm looking at it as a whole distribution, my probability of not hitting the mark is going to be 100 minus 84.61 And essentially, that shaded region then becomes 15.39%. That's saying out of your distribution as a whole that that's my likelihood of not hitting the mark. So you can use the Z table and P table as a way to understand your data and basically take it from a raw score and turn it into an understandable standard metric. Because keep in mind, as we're going through 0, 1, 2, 3, -1, -2, -3, that's a normal standard distribution that we can relate no matter what our variables are. So overall, p-values allow us to understand our performance and efficiency in our process. Now, probability is like a way to guess how likely something is to happen. You know, you calculate by dividing how many good outcomes by the bad outcomes, the good outcomes over all the possible outcomes. So if I was to look at a metric and I said, okay, well, I want to be able to kick a field goal out of 4 times 1 time. So I want to at least have one good opportunity over a total opportunity. And that's going to lead to a probability of 25%. Or when I eat pizza, I eat 3 out of 6 slices, right? And the other 3 slices go to my wife. That's essentially going to be 1 out of 3, or 1/2, which essentially is going to be 50%. That's the probability of something. Now, probability is always going to be put into a percentile. Now, how many sides are on a dice? Well, we're going to have 1 out of 6 sides. 1 out of 6, 0.16, or 16.67%. Now, when I ask you guys, what's the probability of getting a 6 when rolling a 6-sided die 3 times in a row and getting a 6 each time? Well, it would be 1 out of 6, 1 out of 6, and 1 out of 6. Each time I roll that dice, I have a 1 out of 6 chance. Well, when I multiply that, I essentially get 2 out of 16. Or 1 out of 216. Now, 1 out of 216, something's off. Oh, my data's off, right? And so human beings are only going to be about 80% correct in their calculations. I want you to take that in mind as we go along. And this is a part of the exercise because I caught it the other day when I was putting this together for you guys. As a probability, I have 1 out of 6 times 1 out of 6 times 1 out of 6. 1 out of 36. 36 times 6. 216 over 1. Okay, so that part of my equation is correct. But when I turn it into a probability, I actually get a probability of 0.4629%. Now that means that rolling that dice, I'm only going to have a 0.46% chance of them all being the same number value. Well, let me ask you this. What's the likelihood of me not getting that? Well, it would essentially be, 100, or you could just say, you say 100 out of that variable right there. And that's going to equal our 99.54% metric of not hitting that mark. You see how you can interchange those variables? One could be a yield percentage, one could be a defect percentage. The concepts are still there. Now, if I ask you, for example, if you have essentially 10 red marbles, so 10 red marbles out of 5 blue marbles, what is the probability of randomly selecting a red marble? Well, it would be essentially our favorable solution, that's what we want, out of our total outcomes. You get 10 out of 15, 0.667, or 66.67%. Now, if I was to ask you what's the probability of not hitting that mark, again, you would just subtract it from 100. Equaling around 33% chance of not hitting that mark. And a probability, a deck of cards, right? Let's say in a standard deck of 52 cards, what's the probability of getting a heart out of those cards? Well, essentially we're going to look at it, and the probability is going to be 13 because there's 13 cards with a heart on it. And then there's 39 other cards. So you can see the probability of 1/4 and the probability of 3/4. You put those together, they're going to equal 100% of our data. When we look at that, we can interpret it as 13 over 52, which is 0.25, which then turns into 25%. Overall, your probability is a good metric to understand your process. And the fun thing is once you find your Z value, you can find your P value, or let's say you only have a P value to go off of. Well, you could subtract 50% and then find where this value is here, and then go through and reverse engineer it to find your Z-score. In this Excel sheet and your probability of it, let me delete this. As you're looking at this, right, I have your Z-score calculator and what it will equal. And you can reverse look this up and fact check as you're building this calculator. Overall, the p-value lets us know the probability of hitting our mark. So when we talk about Krispy Kreme, a good way to understand our population versus sample. Population is going to be that bigger number, right? The sample is going to be our lower number. So when we talk about Z-scores, the idea here is turning that raw data into an understandable, standardized form, right? And we can look at our Z-scores here as a way to interpret it. right? There's several benefits of using a z-score, and I'll kind of go over it with you here. You have predictive analysis. We can use it in finance and research. We can enhance the accuracy of forecasting models. In performance analysis, it's useful in academic and professional settings, especially if you're doing research models. We assess individuals' performance against the average. We can identify any outliers, and it's useful in data cleansing, right? Understanding our data, and it helps in spotting the outliers, right? Those outliers are typically anything that's 2 standard deviations from the average. And we can use it for standardization, as we can convert scores to a common scale for us to understand. When we facilitate data comparisons, we can understand data at a glance, but we can use z-scores as a performance metrics for continuous improvement. Now, z-scores and how to calculate them are not difficult. Understanding how to calculate z-scores is relatively easy. We use a formula in different ways of approaching it, and we can understand it off of data, or we can use a collection of data to calculate our z-score. Z-scores make it easier to understand distributions, as we can relate it and base it on a scale. If I'm to look here and I say, okay, I have my data and I have the different variables of it. I have my mu, my average, my x bar, and then I have my variations in my process. Well, in this standardized approach, the space in between is only 1 standard deviation. And you can see how we relate it and everything back to a normal standardized scale. If I say, for example, I want to have a probability of 3, and I'll just put it right here. That means I'm filling in and taking in all of this data right here and leaving that little smidget right there. And I'm saying that this is 3, so you guys can see it from that standpoint. That's going to give us a percentage, a distribution of, I think, let me look at it. We have 99.8687%. Well, what's my likelihood of not hitting that mark of a z-score of 3? Well, essentially, I would come over here and say 1 minus 99.87%. And I would get 0.13 percentage chance of not hitting that mark, the red region. We'll look at another example here. as we can use a z-score to determine variability in our process as well. Let's say I have a z-score of, let's say 1, right? That means all of this shaded region is essentially going to be highlighted as green, just to save us time on drawing. With this remaining value of being anything outside that region. What I want you guys to do is to find out, use your probability calculator, and find out what a z-score of 1 will actually represent. What in this is going to be my defect percentage? What's going to be my yield percentage? So go ahead and calculate these variables here. Tell me what my yield percentage is first, and then tell me what my defect percentage is going to be. So when I draw this out, I should have a range. Let me change this. I want to do this a little bit different. I have a yield value of 84.13% with a defect rate that's essentially going to be 0.159%. Roughly. And that's all because we can find and calculate if our z value is equal to a certain number. And you can see how you can relate that back to a performance metric. Now, when we interpret z-scores, I want you to kind of take in mind this formula. You have z equals x minus mu. This, ladies and gentlemen, is always going to be your observation. This is always going to be your, let's say, comparison analysis, or we'll say like your average. A sample data. Right, if I have 5 variables, I can find the average of that and compare it to the observation. And this is just going to be what your deviation is in the process. Don't kill me if I didn't spell deviation right, but so your z-score formula is something I usually tell students to have like essentially tattooed on their hand. You know, it's a good measurement. X is going to be our observation. Mu is going to be usually compared to our sample data. And our sigma is going to be our standard deviation of a sample size. Years ago, when I first started in the range of quality, I started as a quality engineer. I worked for a company that was a subsidiary of Honda. And one of the roles I had to do was, quality testing engine control units, ECUs. Now, in this, I found certain aspects of quality management I liked. I found things that I didn't like. I thought sometimes the structure of things was very hard to communicate issues. right? It was more of a top-down approach instead of, a collaborative approach to quality management. But, basically when we look at this, we manufacture engine control units with a thickness diameter of 0.45. We have the following variations. We have mu, which is going to be 0.42, and we have our standard deviation of 0.01. Well, what is the effectiveness of our process? I want to give you guys a couple minutes, and I want you to solve this. So I want you to find what the z-score is, and then I want you to go through and find what the probability is. So looking at this, we have the following variables, and I want us to take into account. We have to set up our formula, right? And remember, we said our formula is going to be z equals x minus mu divided by sigma. Well, all we're going to do to plug in our variables is say z equals x, which is going to be our observation. We know that's going to be 0.45 minus mu. I know my mu variable is going to be 0.42 divided by the standard deviation, or 0.01. When I say 0.45 minus 0.42, I then get a z-score of essentially 3. Now, I know if I go into my probability calculator and I input the data and I say, okay, if I have 3, that's going to give me a probability of 99.86% with a defect rate of 13.49. And so that's saying, what's the likelihood that we're to draw this part again? Will it be in that specification? Now, you can use that p-table value to also find it as well. Essentially, if I went through, I would find what my variables are, which I would just find 3 on there and then go over 1. There we go. Find 3. I get 0.4987 plus that other 50% of the distribution. And then I get an overall effectiveness of 99.87%. So as you look at data and probability, it's a good way to understand and use z-scores to relate that data.